Written by AI. Understanding Decentralized Censorship-Resistant Mesh Networking and the Possibilities of Open Radio Spectrum. Introduction. Reimagining Connectivity Beyond Central Control. In today's digital world, most internet and cellular connections depend on centralized infrastructure controlled by a few large companies or governments. These centralized systems come with inherent limitations, high costs, limited competition, privacy concerns, vulnerabilities to censorship, and uneven coverage that often leaves rural and marginalized areas underserved. As our dependence on digital communication grows, so does the need for new models that transcend this centralized control. The rise of decentralized mesh networking, powered by advances in 5G technologies, new wireless protocols, and open-source software, opens the door to a system where connectivity is no longer owned by corporations but by the very users and communities that depend on it. Such networks are self-healing, scalable, and censorship-resistant, all built around devices communicating directly with one another over a dynamically constructed web of local connections. Even more revolutionary is the idea of freeing the radio spectrum, the invisible wireless resource that allows our devices to talk to each other. Traditionally, governments have tightly regulated spectrum to avoid interference and commercial monopolization. But what if these constraints were removed or radically loosened? How would our digital freedoms, innovations, and social communications transform if anyone could access the spectrum openly without bureaucratic hurdles? This article offers a technical yet approachable explanation of decentralized 5G mesh networking, how it functions, its societal promise, particularly censorship resistance, and the powerful impact of spectrum freedom on the future of technology. The problem space: centralized telecom and internet control. Before exploring mesh networks, it's crucial to understand the limitations of the traditional approach. Centralized infrastructure. The backbone of cellular and broadband service consists of high-powered base stations, fiber backhaul, and data centers owned by telecom companies. Building, maintaining, and expanding these networks demands enormous investment, incentivizing monopolistic behavior and limiting competition. Limited spectrum access. Governments allocate specific frequency bands to carriers via licenses. These licenses are expensive and limited in number, creating artificial scarcity. Those without licenses are barred from transmitting, limiting innovation and community networks. Vulnerable to censorship and surveillance, content and connectivity are routed through controlled infrastructure. This centralized control enables providers, and often governments, to monitor, throttle, or block data flows, undermining privacy and freedom of expression. Cost and coverage inequalities. High setup and operational costs lead to expensive service, while rural or poor regions often lack coverage because they aren't profitable markets. Single points of failure. Because networks rely on fixed centralized infrastructure, outages or attacks on key points can disrupt service for vast user populations. Given this context, a new paradigm is needed, one where communities deploy and own their networks, and devices cooperate to build resilient, censorship-resistant connectivity. What is mesh networking? Mesh networking creates a distributed network unlike traditional star topology cellular networks where all traffic routes through base stations. Instead, in a mesh topology, each device acts as a node that can receive, transmit, and relay data. Nodes communicate directly with neighbors, passing data hop by hop to the final destination. There is no single central hub driving the network. The network self-organizes and self-heals if nodes move or go offline, finding alternate routes for data. The system can scale organically simply by adding more nodes. This concept isn't new. In fact, mesh networks have been used in military, emergency, and sensor networks for decades. What's different now is applying mesh principles to cellular-scale 5G networks plus Wi-Fi, alongside integrating open-source 5G core software and leveraging modern smartphone capabilities. Technical advances enabling decentralized 5G mesh networks. 1. 5G standards including mesh capabilities. Since Release 16 of the 3GPP 5G New Radio (NR) standards, native mesh networking features have been introduced. Device-to-device D2D communication. Devices can talk directly without routing through a base station, useful for proximity services. Multi-hop mesh topologies. Devices can relay data across multiple hops to reach more distant points, extending coverage and resilience. Dynamic routing protocols. Networks dynamically calculate optimal paths to route traffic considering latency, link quality, and node availability. These capabilities break away from the traditional cellular model where every device must connect to centralized base stations, enabling decentralization at the radio layer. 2. Open source 5G core networks. The 5G core network is the software backbone managing connections, user authentication, session control, and data routing. Historically, 5G cores have been proprietary and tied to carriers. However, projects like Open 5G Core, Open Air Interface (OAI), Free 5GC have developed modular, 3GPP compliant open source implementations of the core network. These allow anyone with spectrum and hardware to deploy standalone 5G networks, whether private or public, removing the need for traditional cellular carriers. 3. Smartphones as mesh nodes. Modern smartphones have powerful radios, processors, and software platforms capable of acting as mesh nodes. With appropriate firmware or applications, devices can discover neighbors, establish secure encrypted multi-hop routes, relay others' traffic, contribute to network capacity and redundancy. Running mesh protocols transparently in the background enables phones to form a collaborative, distributed network without special hardware. 4. Hybrid mesh networks, 5G plus Wi-Fi. 5G mesh offers wide area coverage using licensed or shared cellular spectrum, suitable for outdoor environments. Wi-Fi mesh excels in local, high-bandwidth environments, dense indoor areas or neighborhoods. By integrating these two, a heterogeneous mesh network emerges where 5G covers broad outdoor regions. Wi-Fi handles dense local environments. Devices switch seamlessly to the best available link. This hybridization maximizes coverage, throughput, and reliability. 5. Advanced radio and protocol technologies. Several engineering innovations underpin efficient mesh operation. Beamforming and directional antennas to focus signals and reduce interference. Cognitive radio capabilities for dynamic spectrum access and interference avoidance. Multipath routing algorithms intelligently balance traffic across diverse paths. Low-power adaptive radio modulation maximizes energy efficiency. How decentralized mesh networks empower censorship resistance and privacy. Mesh networks disrupt centralized control points by design. No central choke points. Data routing dynamically shifts to avoid potential black holes or censorship gateways. End-to-end encryption. Communications are encrypted at the source, preventing intermediate nodes from reading content. Anonymous addressing schemes. Devices use cryptographically generated ephemeral network identifiers to avoid persistent tracking. User sovereignty. Individuals retain control over their keys and data identity, without centralized authorization or vetting. This architecture makes the network inherently resistant to technical censorship, intrusive surveillance, and network shutdowns. Open radio spectrum. The ultimate freedom for network innovation. Understanding spectrum scarcity and regulation. The radio spectrum is a finite range of electromagnetic frequencies used for all wireless communication. To prevent chaos and interference, governments typically allocate specific frequency bands via licenses. However, this regulatory model creates artificial scarcity, gives power to incumbents who pay for exclusive rights, prevents grassroots, experimental, and community networks from flourishing. What would change with unrestricted spectrum? If regulatory constraints were removed or relaxed, allowing anyone to use any frequency within technical limits, massive innovation would occur. No licensing costs or bureaucracies would empower inventors, hobbyists, and communities worldwide. Unprecedented decentralized networks would emerge. Devices could use dynamic spectrum sharing to avoid interference collaboratively. Freedom from censorship and monopolization. No single entity could control the wireless environment. Global digital inclusion would expand. Networks could cover rural, underserved, or economically disadvantaged areas cheaply and flexibly. Technical challenges without spectrum limits. Interference. New algorithms would be needed for intelligent spectrum sensing and dynamic channel selection to prevent jamming. Power management. Devices must adapt transmission power to avoid overwhelming neighbors. Coordination protocols. Mesh devices would self-organize harmoniously despite overlapping spectrum usage. The societal and political implications. Freeing spectrum and embracing decentralized mesh networks aligns with digital democracy. Users govern their networks and data without corporate or governmental gatekeepers. Resistance to repression. Privacy and free speech safeguarded by open, censorship-proof architecture. Economic empowerment. Lower costs and new local business models replace monopolistic incumbents. Disaster resilience. Autonomous mesh networks remain operational even during infrastructure collapse or outages. Real-world implementations and movement towards decentralization. WirePa's 5G mesh, an industrial-grade, ultra-reliable, license-exempt mesh network serving thousands of devices with self-healing, decentralized routing. Meshtastic. Open-source community mesh projects enable off-grid communication using affordable radios. Open 5G core projects empower small parties to operate local 5G networks. Pirate Party and Anonymous Legion. Political advocacy groups promoting digital freedom, privacy, and spectrum openness. Navigating the path forward. Challenges and opportunities. To advance decentralized mesh networking and spectrum freedom, key steps include spectrum policy reform. Governments adopting community spectrum licensing, license exemptions, or shared spectrum models. Device and protocol innovation. Improving mesh protocols for scalability, security, and user-friendliness. Open source software development. Creating robust, modular, interoperable stacks across hardware platforms. Security frameworks. Design resilient authentication, anti-abuse, and encryption technologies. User experience. Designing seamless mesh operation running transparently in consumer devices. Global collaboration. Cooperation between engineers, activists, regulators, and communities. Closing vision. A decentralized, resilient digital commons. Decentralized censorship-resistant mesh networks combined with unrestricted radio spectrum access represent a profound shift in our relationship with communications technology. They promise to transform the Internet and cellular networks from centralized utilities into democratic commons, tools for freedom, inclusion, innovation, and privacy for all. The technology is feasible today, thanks to advances in 5G mesh standards, open-source software, and device capabilities. The key remaining barriers are social, political, and regulatory. Working together across disciplines and borders, we can build these networks into reality, creating a truly connected world free from corporate monopolies or governmental censorship.